we are having the next presentation from Dr. Hartig. He is coordinator in additive manufacturing for the German Navy, so the Deutsche Marinekommando. We're good to have you here, and we are really interested in what you will tell us about the newest developments in the resource-based AM framework for the military sector. Please welcome.
Yeah, thank you very much for the warm welcome. I want today to talk to you about navigating the future, lessons learned, international standards, and the path forward. Actually, the picture is not real at the moment. I don't know if you saw it, but we do not have that much printers on board, just some. So, first of all, if it's working, oh, that's too much. Yeah. As said, my name is Lieutenant Dr. Sascha Hartig. I'm the head of engineering principles and additive manufacturing. All these ships in these pictures are not just for getting the presentation nicer. All these ships I served on, and on some of them I also had a printer. So we have a lot of experiences how printing on board works, and I will give you some glimpse on our experiences on that. So it's really long. Okay. Our lessons learned. So I want to start with use cases, because use cases are mostly the most interesting things. And I want to show you that we don't have a lighthouse project like additive manufacturing. We have a lot of everyday use cases we are solving on board. It's nothing really special in the end, like a rocket engine, something like that. It's just small plastic parts which do matter and which make a difference. So one part is this poppet valve from the gray water system. So if you're washing your hands, for instance, on board, you have the gray water system, and to get the water coming from the wash basin, you have to have some components from with a vacuum system. And in this system, you have this assembly, and in this assembly there's a poppet valve. And the problem is that the lowest logistical addressable unit is just the assembly. But we are in need of this small poppet valve. So we have a lot of these blue assemblies on board missing the poppet valve, because just the poppet valve is breaking. It's in that direction. And what we did some design tweaks to this poppet valve, and then we printed it with an MEX printer, and it's better than the original. And we just print the part we are in need. Another use case, if you're thinking about interim parts or special repairs. In this instance, we had to remove the heat exchanger from the seawater system. And seawater cooling system, these are pipes like this size, and there's a lot of water going through. And the big problem was that the shut valve, which is behind that seawater pipe, didn't hold tight. And then we got 180 liters water into the ship, and this was some kind of a problem, because if you're on a ship, you don't want to have the water in your ship. So what did we do? First of all, yes, we had a bucket solution, but this is all still not holding tight. Then we printed overnight this blind flange, and it did hold tight. So this is like for immediate repair, a solution where we are using additive. Another thing is obsolete parts. We have electronics which are old, sometimes older than me. And the problem is that the original equipment manufacturer, they don't want to support us anymore. And in this special case, it was this electronic cards holder, and it's made out of ABS. And ABS, after 10 years, it gets brittle. It's okay, it's no problem. But we do not get the spare parts from the original equipment manufacturer. So what we did is we designed the part with CAD and then printed it with an MEX printer. And now we can use this obsolete electronics for some more years. Hopefully we will get the new electronics then soon. And next thing is, everyone is speaking to me and say, do you use metal printing? And for us at the moment, the main focus is on polymer parts, because the biggest amount of use cases we have at the moment are polymer parts. And polymer parts do matter. And this is one particular use case from that. If you're thinking about, it's just a fan from an electric motor. But if this electric motor is connected to the fire extinguishing pump, and you got just 4 of these fire extinguishing pumps on board, you're losing 25% of your fire extinguishing capacity, which is a really important thing if you're thinking about operational readiness. So polymer parts do matter, and they are really in high focus for us. Another thing is we want to give the soldiers a tool to realize their ideas. In this particular case, the operational officer from the operations center of the COVID came to me, and he has a board, he called it fighting board. On this fighting board, he has all the warnings, for instance, mine warning, air warning, whatever. He needs to keep track of the operational area and what warnings we have. And the problem is that this board, he's always carrying it around, and he has no hand-free. And what we did, we made a holder for this fight plot, so he has one hand-free. And the good thing is also for the radar operator who's sitting in front of him, he doesn't get the board onto his head, so he's also really happy with the solution. Another use case for level 2 additive manufacturing, so with bigger parts and industrial polymers. In this case, we used polyamide, so nylon 12. We used it to print a sea filter. So the big problem with these sea filters is the original part is made of metal, and because it's metal, one thing has to corrode, either the gasket or the housing, or the filter. And the problem is, if you have a corroding filter and you want to clean it from all the shells and the stones which are coming into the seawater system, if it's corroding and you're taking like a hammer or something like that, holes get bigger and bigger, and holes like that, it isn't a filter anymore. So if we are on a sea trial or something like that, mostly we have 2 of these sea filters with us. But with a polymer sea filter, this isn't corroding. This is the bad thing about plastics, but the good thing for us, nothing happens to this. And the good thing is, because it's out of nylon, you can use a hammer for cleaning it. And it's really working really well. So you think, this is our also lessons learned presentation. So first time everything right? No. We had a lot of troubles also with the printers we have implemented. And we had some problems with the tubes going to the extruder. We had some parts which did not stick to the build plate. This is what you experience. Nothing goes the way you intended to have. And even with additive manufacturing, you will have your problems. And you have to solve them. Also, some parts not aligning with each other. But that is what you have to tackle, because the overall goal, what we want to do is, if we are in a self-sufficiency phase, so between port A and port B, we want to have this phase not interrupted by missing a part, missing a spare part, for instances. And we can use additive manufacturing either for a temporary replacement part, so we can get a system back online really fast. But we can also use it for manufacture expandable items. So we want to extend the self-sufficiency phase with additive manufacturing. So what are our lessons learned? First of all, you have to have a comprehensive strategy, because if you want to have success in AM, you have to have this holistic strategy and also these lessons learned, and you have to do, or you have to improve the whole concept and the whole process. You have to have collaborative innovation, so foster a culture of knowledge sharing. And also, I think this is really important on an international level. Everyone is investing in additive manufacturing. Everyone is buying machines. Everyone is making his own experiences. It would be really good if we share what did not work, because if we share this kind of experiences, other people can spend their resources more carefully, not making the same mistakes in the end. Training is vital. We are investing a lot of our resources into training, because this is really important. If you do not have soldiers which are really into additive manufacturing and know what way you're doing, you're missing a multiplier to share this technology and what you can do with this technology. And data management is a challenge and opportunity in the same time. So if you're thinking about how to get back the data from the printers on board, for instance, this is a really important thing, but it's also really hard to establish this. And overall, the most important thing, don't demotivate your personnel by complicating simple things. Additive manufacturing is supposed to be easy to use, easy to design something, print something, and in the end use something. We are really good at complicating this simple process by, for instance, documentation or something like that. I know it's needed, but it should be kept simple. So when we are thinking about our implementation at the moment, so what we are doing in the armed forces, and for me the focus of course is the German Navy. We have a lot of these categorization systems for polymers, metals, and other things, and it is hard to keep track and keep track all of the processes which are available at the moment in the industry. And if we are looking at the armed forces, all the processes which are marked in red are processes we have integrated. And even for us, it's difficult to connect the dots between processes we are in need and which of these processes are really good for the use cases we have at the moment. So the big problem is that on the one hand side, you got your additive manufacturing experts, which know which kind of process you have to connect. And on the other hand side, you have people who are thinking about additive manufacturing or 3D printing like it's a wand, for instance. You can make everything with it. Then you have the other kind of people who are thinking 3D printing is just making toys with plastics. And you have to have something in between. If you're talking about additive manufacturing, there has to be like a categorization system, how you can categorize that. And we are looking in this particular problem with from the side of resources. How much resources do we have to put a machine somewhere like a ship, for instance? So a small ship where we do not have a lot of space, for instance, where we do not have a lot of capacity from the soldiers, for instance. And the big problem about that, come on, is that you have to connect the dots. So you have on the one hand side AM processes, on the other hand side you got use cases. And in between where's the user? And this is a knowledge-driven process. If you know which kind of machine you have to connect to the use case, then you can solve your problems or solve this particular use case. And what I suppose, it's looking more like a mess, and if it's coming, it's really long line today. Okay, and if you're routing these connections between like these tunnels, categories, it looks a lot more like a mess. But if you're tightening these connections, you get categories for additive manufacturing regarding the resources. And if you're thinking about, this is a knowledge system, if you're thinking about the future, and you see where are new AM processes on the market and where are new use cases, you have a category where they fit. And if you're thinking about new processes coming to the market, you can either also look into which kind of use cases could you improve with this new process. What we are doing is we are trying to keep or trying to make an ISO norm with that. It will be the ISO 52966 regarding an AM level system for temporary self-sufficient systems. And with this ISO, we can tackle this problem of it's not just 3D printing and it's not just about the processes. It's like additive manufacturing levels and looking from the resources side. So what we did, we took the education, integration restrictions, AM machine requirements and possibilities, and we thought about what level does what level has what kind of possibilities regarding the restrictions. So if you're thinking, for instance, I'm a former submariner, if you're thinking about if you want to print on board of a submarine, you do not have space, you do not have people, for instance, and therefore you just have limited access to resources, just simple equipment what you can install, for instance, and just doing prototypes. So this is what we are thinking and using at the moment for our implementation in the German Navy. It's not good working today. So what are the benefits from this standard? First of all, you have interoperability, common AM practices and data formats for enhanced collaboration. We want to have efficiency in the streamlined workflows, a more resilient network. So we are thinking about if we are in together with the Dutch Navy, for instance, that if we do not have the capabilities and our partners have the capabilities, yet then just print together and solve things, because the overall readiness of the whole strike group is more important than just one ship. The other thing is we want to have this kind of knowledge sharing, and by using ISO standardized categorization system, we can easier share also the knowledge between each other. This is one of the or this is the norm which will hopefully be published next year. Okay, so what did we do? Yes, last year at EDA AM Village, we had a workshop with this AM level system, and we took the idea from how to categorize regarding the resources, and we gave the people, the participants at the AM Village, the opportunity to how they do interpret these kind of idea. And the interesting thing, if you're thinking about this table I showed to you, and then what we did is a workshop, and you see, yeah, it's the same. It's the restrictions, what kind of use cases, where to use them. And this was done by the participants of this workshop. And if you're thinking ahead, then you also can start with which kind of process or action you can fulfill in each level. So for instance, we had a part which was really complicated in this case. We had just part inspection on level 1, but then we had to give it to level 2 because design was really, really hard to do. And then you can start to make like these production plans, also production plans for additive manufacturing in this level system. So what I then did is, this is my research side. So yeah, we are now looking into the future, and this is more from my research side with the Federal Armed Forces University in Hamburg. So what I did is to take these levels of additive manufacturing, and you can think of it like all these small bubbles are use cases, and the diameter is the complexity of a use case. And if you're having this funnel, every funnel has a sieve. So this is like operational control, and I want to let's think about that at a moment. So if you have a use case with a small complexity, and you have the sieve with a bigger hole, it will fit into it. And what that means is you have a use case which is that easy then that you can print it, for instance, on board. And this is what the system is about. You have to have like the operational control for each level. What can you print on this level? And this is really, really looking into the forward. What I did is I used this funnel sieve model and created a ChatGPT-like model to. The big problem is that you have like this complexity. How do you measure complexity? And this is really a hard thing to do with parts. And what I did is then in the end I created a system which is categorizing the like the part size, post-processing, and so on and so on. And I make a part vector. And it's hard to make this part vector, but the easy thing is then with you can have a dialogue with ChatGPT, and he's asking you about the part, and in the end you get a part vector which you then can use to get the complexity level from a part. This is open, so everyone can use this ChatGPT model, and if you would like to have the link, it's either on my LinkedIn page, so try it out, and we have a dialogue about that. I see my time is up. I'm really sorry for that. I'm here also for the whole evening and tomorrow. So if there are any questions, now's the time. Thank you very much. Sorry for being a little bit over time.